Okay, is it clear? Any questions on this? Yes?
So here we have assumed that the A is not dependent on the design variable S, right?
Yes, here we assume A is not dependent on design variable S. How do I fix that? How do I go to the more general case that if we have a linear equation that the matrix itself may be dependent on the design variable? Or even a more general case, we have a nonlinear function f that is a function of x and s equal to 0. Right? What if we have a nonlinear algebraic system? We need to solve using Newton's method, or quasi-Newton's method. That includes the case Xun has just asked about, right? What if the matrix actually depends on S? We are going to be now talking about this case. And again, and another thing is J is not necessarily a linear functional. J may be a nonlinear functional of X. And let's assume the simplifying case J is a linear function, a nonlinear function. Right, so now both the governing equation and the objective function are nonlinear, are potentially nonlinear. Again, the question is how to compute partial J, partial S without having to solve equations like that repeatedly. Okay, any ideas? Huh?
The big F, is it a function, a vectorial function, or
Which one?
F?
F. Okay, yeah, good question.
Or is it scalar function?
F is a vector function. F is a function that has as many rows as there are axes. So here, F fully determines X for each S. Right? What does this mean? That means how many of you knows implicit function theorem? You know. Okay. So the implicit function theorem says that if partial f, partial x, let me use a different color. That implies that partial f, partial x is a non-singular square matrix. The fact that it is a square matrix means that F has as many entries as there are axes, right? And it has to be non-singular. If it's singular, then X is not well determined by this. All right. So the implicit function theorem says that if I have a nonlinear function f, and around the solution, around where f(x) and s equal to 0, my Jacobian of f with respect to x is non-singular, then in this neighborhood, in the neighborhood of s, I can change s, and for each s there is a unique solution x that corresponds to the solution of this equation. So the solution exists for a range of s, and x is uniquely determined by s within that range. All right. Okay, back to the question of how to compute partial j, partial s. Any ideas of how do we borrow what we used in the linear case? Yes?
you solve partial f for x transpose phi is equals to minus partial j over partial s.
Partial j,
Partial j over partial x.
partial x. Okay, good. How did you came up with that?
There is a trick.
Huh?
There is a trick.
There is a trick?
Generalization.
You can consider introduce a Lagrangian, just a constraint, and then you just say that all the derivative of the Lagrangian must be 0.
Wow, you are very good. Okay, so I'm going to illustrate the trick to everybody. So the trick, as you said, is called the method of Lagrange multiplier. It is augmenting the objective function. So g of x is the objective function, right? It is basically saying g of x is equal to g of x plus 0. Everybody agrees with that? And I'm going to expand that 0 as f, because f of x and s is equal to 0, right? Agreed? Okay. F of x and s is equal to 0, and also f of x and s, well, it is a vector, so this vector times any phi transpose times f is equal to 0. That is true for any phi. Agreed? Okay. But then I'm going to take the derivative of j. I'm going to look at a small perturbation of j as a result of a small perturbation in s. So let's say I have a small perturbation in s, I call delta s. That small perturbation, if I push it through the differential equation, if I plug it into the differential equation, causes a small change in x, delta x. And that small change in x causes a corresponding small change in j. Okay, I'm going to look at what is that small change in j. That small change in j, according to this equation, is equal to partial j partial x times that corresponding small change in x, right? And also this equation tells me that I can add this. I can add a phi transpose times a small change in f, which is equal to partial f partial x times delta x using chain rule plus partial f partial s times delta s. Actually, this equation, the parenthesis equal to 0, establishes the relationship between delta s and delta x. In order for the f to be 0 before and after the change in delta s, I need this parenthesis to be equal to 0. Right? This is equal to 0 basically means delta f is equal to 0 after the change in delta s and corresponding change in delta x. Agreed? And remember, this equation is true still for any phi. Now, like what I did in the linear case, I want to be able to represent the change in the objective function in a way that does not involve the solution. I want to represent delta j as an equation that does not involve this delta x. I want to get rid of this delta x also here within this equation by choosing a particular phi. Or I want to construct such a phi that makes the coefficient on delta x to be 0. So delta x is cancelled out of the equation. So if I combine the terms, I have partial j partial x plus phi transpose partial f partial x times delta x. This is what is multiplied on delta x, which I want to set to 0, plus phi transpose partial f partial s times delta s. So that is the adjoint equation. This is the adjoint equation, right? I think I also need a transpose over here. Now this is the adjoint equation that removes the delta x term from the sensitivity equation and allows me to compute the change of delta j directly as a function of delta s. So after solving for phi, my partial j partial s is going to be equal to phi transpose times partial f partial s, because I have contribution only from this term. Yes?
Now check your battery. It's seems to be low.
Oh, 20%. Oh, okay. Thanks. Don't know. I don't know what I'm doing. Okay. Any questions on this? So the procedure is that we need to first solve the nonlinear equation just once for x, because usually we need that x to be able to compute partial f partial s, partial j partial x, partial f partial x. So these three partial derivatives usually depend on the solution x. And once we have these partial derivatives, that enables us to solve this adjoint equation. Once we have that adjoint equation, we can compute the sensitivity derivative using the adjoint solution for as many s as I want. All right. Questions? Now we have been still doing all of that in the discrete world, assuming we have discretized everything, right? But we can also do that in the continuous world.